Welcome back to the deep dive. Today we're looking under the hood.
Or, well, where the hood used to be anyway.
Right, exactly. We're looking at this totally invisible revolution happening inside electric vehicles. And I want to start with a paradox that just kept popping up in the research stack this week.
I think I know exactly where you're going with this. It's the heat problem.
Yeah, the heat problem, because once you see it, you really can't unsee it. In a gas car, heat makes perfect sense.
Oh, absolutely.
You are literally exploding dead dinosaurs to move heavy metal pistons. So explosions equal fire, and fire obviously equals heat.
Right, it's a combustion engine.
Exactly. But in an electric car, there's no fire. There's zero combustion. So why, according to all these engineering reports we read, why are EV designers absolutely obsessed with cooling systems?
That's a great question.
Why do electric cars generate so much heat if they're supposed to just run on clean energy?
It feels like a total contradiction, doesn't it?
Yeah.
You kind of expect an EV to just run cold, like your phone.
Right, like just a battery and some wires.
But that heat is actually the major clue. It leads us straight to the most critical component in the entire vehicle. And surprisingly, it isn't the battery.
And it isn't the motor either.
Nope.
That is exactly what we're digging into today. This component is called the inverter. And honestly, before reading this tag, I just thought of the inverter as, well, just a box.
Like a generic part you just buy off a shelf somewhere.
Exactly, just a piece of hardware. But the sources argue that the inverter is actually the brain behind the brawn. And more importantly, the materials inside that box are shifting from standard silicon to some really exotic stuff.
Yeah, exotic is putting it mildly.
Right. We're talking about silicon carbide and gallium nitride.
The research refers to these as wide-bandgap semiconductors. And I know that sounds like incredibly heavy jargon.
It really does.
But it's actually the key to literally everything you want from an EV. Faster charging, longer range, and ultimately lower costs.
So let's just start with the basics here. What is the inverter actually doing in the car? Because the research describes this. They call it a fundamental language barrier inside the vehicle.
I love that analogy. It's a really great way to visualize it. So you have two main players in the powertrain. On one side, you have the battery.
Okay.
The battery is just a storage tank. It releases energy as direct current, or DC. And DC is a very steady one-way flow of electrons.
The sources compared it to a river, right? Just flowing smoothly downhill.
Exactly. A steady, constant flow. But on the other side of the car, you have the motor. And for high-performance vehicles, which is basically every modern EV on the road today, the motor is almost always a three-phase alternating current engine, an AC engine.
Which raises the obvious question, why not just run the motor on DC, like a toy RC car?
It comes down to efficiency and durability. AC motors are usually brushless, so they don't wear out as fast. They're way more powerful for their weight, and they are just much easier to control precisely.
But they run on alternating current.
Right. Electrons that wiggle back and forth rapidly. So the battery speaks DC, and the motor speaks AC. They literally cannot talk to each other.
Enter the translator.
The inverter. It sits right between them. It takes that steady river of DC from the battery, chops it up. It flips the polarity back and forth thousands of times a second to simulate an AC wave.
So without the inverter, the car is essentially just a very heavy brick.
It doesn't move a single millimeter.
This brings us to a concept the sources called the electronic accelerator. And they made a really interesting point here that I want to highlight.
Go for it.
They said we need to stop thinking of the gas pedal as a mechanical valve, because in a gas car, you press the pedal, you mechanically open a throttle body, more air and fuel go in, and you get a bigger boom.
Right, it's a very mechanical direct link.
But in an EV, the pedal is basically just a request form.
That's a great way to put it.
You're sending a digital signal to the inverter's computer saying, hey, I would like to go faster now. And the inverter then has to decide how to actually make that happen by manipulating the electricity.
Yes, and it manipulates two specific things, frequency and amplitude.
Okay, let me make sure I got this right. Frequency is the speed of the switching rate.
Yes. Think of the inverter like a conductor standing in front of an orchestra. If the conductor waves the baton faster, increasing the frequency, the music speeds up.
So in the car, increasing the frequency of the AC current makes the motor spin faster.
Exactly, that is your speed.
And amplitude is like the volume of the orchestra.
Precisely. Amplitude is the amount of power or the sheer current behind each of those waves.
Right.
If you stomp on the pedal at a green light, you aren't really asking for high frequency yet because you're starting from zero.
Right, you're not going fast yet.
But you are asking for massive amplitude. You want torque. You want the loudness of the current to be at its absolute maximum.
So the inverter is doing this crazy juggling act constantly.
Right.
It's adjusting the speed of the switching and the power of the current simultaneously, just based on whatever your right foot is doing.
And keep in mind, it's doing all of this while handling hundreds of volts and hundreds of amps. It is a incredibly stressful, violent environment for a tiny electronic component to live in.
Which brings us to a feature that I think still feels like magic to a lot of people.
Mm.
Regenerative braking. Because this inverters, it isn't a one-way street.
No, it's bidirectional. And regenerative braking is honestly the closest thing we have to a free lunch in physics.
So when you take your foot off the accelerator, what is physically happening inside that box?
The momentum of the car keeps the wheels turning right,
Sure, you're just coasting.
and the wheels physically turn the motor. So now instead of consuming electricity, the motor is acting like a generator. It's creating this wild, chaotic AC current.
But the battery can't accept AC.
Right, if you sent that raw AC straight into the battery pack, you would destroy it.
Oh, wow.
So the inverter has to instantly switch roles in a fraction of a second. It catches that AC coming from the motor. It rectifies it, which basically means calming it down and straightening it out back into DC, and then pushes it back into the battery pack.
You are actively refilling the tank just by slowing down.
You are. And the inverter also determines how hard that braking actually feels to you, the driver. If the inverter tries to grab a massive amount of energy really quickly, the car slows down aggressively.
Like one pedal driving.
Exactly. But if it just sips the energy, you coast more naturally. The inverter entirely controls the feel of the drive.
Okay, so we've established that the inverter is the MVP of the car. It's the translator, it's the conductor, it's the refueler. But the research documents we read highlight a major, major problem with how we've been building them. They call it the silicon ceiling.
Yeah, the silicon ceiling. Because for decades, the entire electronics world has run on standard silicon, specifically a type of switch called an IGBT.
We don't need to get bogged down in the acronyms right now.
No, definitely not. You just need to know that silicon as a material is essentially a bit leaky.
Leaky in terms of energy.
Yes, exactly. Every single time you flip a switch, and remember the inverter is flipping these switches thousands of times every second, you lose a tiny little bit of energy. Engineers call it switching loss.
Makes sense.
And then while the current is actually flowing, you have what's called conduction loss, which is basically just electrical resistance.
And as we know, resistance creates heat.
A lot of heat. A really good traditional silicon inverter might be 95 or 96% efficient.
Which honestly sounds pretty good.
It sounds great on paper, but when you are pumping 300 kilowatts of power through it, that 4 or 5% loss is massive. It's like driving a gas car with a hole in your gas tank.
And that waste heat is the exact reason for all those heavy cooling systems we talk about at the very beginning of the show.
Exactly. You have to get rid of that heat somehow, or the chips will literally melt into slag. So engineers have to add water pumps and radiators and liquid coolant and thick, heavy copper cabling.
All of which adds weight to the car.
And weight is the ultimate enemy of range. So you end up trapped in this vicious engineering cycle. The silicon is inefficient, so it gets really hot. To fix the heat, you add weight. The weight makes the car less efficient to drive, so to get your range back, you need a bigger battery.
Which just adds even more weight.
Correct. The industry hit a wall. To make better EVs, we didn't just need better batteries, we actually needed a totally different kind of switch. We needed materials that could handle higher voltage and switch way faster without getting so hot.
Enter the aliens.
The wide bandgap revolution.
Let's break this down for everyone listening, because this is where the chemistry gets really cool. The research highlights two specific materials that are stepping in to replace silicon. The first one is the heavyweight champion, silicon carbide or SiC.
Silicon carbide is fascinating stuff. It's a synthetic crystal. They synthesize it at incredibly high temperatures. It's almost as hard as a diamond.
Wow.
But its real electrical superpower is its bandgap.
Okay, I want to pause on this word bandgap. The sources mention this term constantly. How do we explain this simply to someone who isn't an electrical engineer?
Think of the bandgap as a wall that electrons have to physically jump over to conduct electricity. Standard silicon has a very low wall. It's super easy for electrons to jump over, which is why it's a great conductor. But it's also very easy for electrons to sort of leak over that low wall when the chip gets hot.
So standard silicon gets unstable at high temperatures?
Exactly. It loses its ability to block current when you want it off. Silicon carbide, on the other hand, has a wide band gap. It has a huge wall.
Okay.
It takes more energy to start the flow initially, But once the current is flowing, it is incredibly stable.
Hmm.
It can withstand massive voltages. We're talking 800 volts or more without flinching, and it can operate perfectly at temperatures that would turn standard silicon into a literal puddle.
The voltage part seems crucial here. We keep seeing the auto industry moving from 400-volt systems to 800-volt systems. Why does that actually matter for you driving the car?
Charging speed. That is the #1 headline benefit. To charge a battery incredibly fast, you need to push a massive amount of power into it. And power is just voltage multiplied by current or amps.
Right, basic physics.
If you try to push high amps, it creates a ton of heat in the charging cables. They get heavy and hot. But if you push high voltage, you get all that power without the massive heat penalties.
So if you want to pull into a station and charge your car in 15 minutes instead of sitting there for 45, you absolutely need high voltage.
Right. But a standard silicon inverter cannot handle 800 volts efficiently. It requires way too much heavy insulation and protection. Silicon Carbide, though, loves 800 volts. It's completely comfortable there.
And the research points to Tesla being the pioneer here, right?
They took a massive gamble. Back in 2017, with the launch of the Model 3, they switched their main inverters to silicon carbide. The rest of the industry thought they were crazy because the material was so expensive.
But it worked out.
It did. Because the silicon carbide made the car so much more efficient, Tesla could get more miles of range out of a significantly smaller battery. So they actually saved money on the expensive battery pack by spending a little more money on the inverter chips.
It's a brilliant trade-off. Now, there is a second material mentioned in the sources. We called Sicky the muscle, but the second one is the sprinter, gallium nitride or GaN.
Gallium nitride is the new kid on the block in automotive, but you actually probably own some GaN right now in your house.
Yeah, laptop charger, right?
Yes. You know how laptop power bricks used to be those huge, heavy, hot things you'd trip over?
Yeah, totally.
And now they're just these tiny little cool cubes that plug straight into the wall. That space-saving magic is gallium nitride.
So what is GaN's specific superpower compared to Sickio?
Speed, pure switching speed. If silicon carbide is the heavy lifting muscle, gallium nitride is the Olympic beaster. It can turn electrical current on and off literally millions of times per second with almost zero switching loss.
So where does that fit inside an electric car?
It's mostly targeting the onboard charger. That's the specific component that takes the raw AC electricity from your house wall outlet and turns it into DC so the battery can store it. And GaN is also used in the DC to DC converters.
Why do you need it to switch so incredibly fast, though?
Because when the GaN chip switches that fast, you can drastically shrink all the other physical components around it.
You mean like the capacitors and magnetics?
Exactly. The faster the switching frequency, the smaller those heavy copper coils and chunky capacitors can be. The research suggests that using GaN can reduce the physical volume of these power electronics by up to 50%.
50% smaller is huge in a car. That's space you can give back to the passengers for more legroom or put into a larger frunk or honestly just use to make the car smaller and more aerodynamic overall.
It's all about miniaturization. It allows designers to tuck these powerful electrical components into weird little corners of the chassis that were previously completely unusable space.
So putting it together, we have silicon carbide handling the ultra-high voltage heavy lifting of the main drive motor and gallium nitride shrinking down the charging systems. It feels like a complete foundational overhaul of the car's nervous system.
It really is, and the ripple effect is that it's shaking up the global supply chain too. We are seeing a major shift away from traditional Silicon Valley to, well, a very new kind of valley.
The Italian connection, this part of the deep dive really surprised me. The research specifically highlights Catania, Sicily of all places, as a sort of center of the universe for this new technology.
It's become a massive hub. STMicroelectronics has a giant mega campus operating there. And the key term the sources kept using to describe their strategy is vertical integration.
From crystal to module, that was the phrase, right?
Right, because making silicon carbide is incredibly difficult. Growing these synthetic crystals takes weeks. It is not like standard silicon where they can just pull a giant shiny ingot out of a vat in a single day.
Oh, wow. I didn't realize it took that long.
Yeah, cyste crystals grow very slowly, atom by atom, at temperatures that are hotter than molten lava.
So if you are a chip maker and you have to buy those raw wafers from some other company, you're highly vulnerable.
You're vulnerable to supply chain shortages, to geopolitical issues, and to massive quality control problems. So STMicro decided to do absolutely everything in-house, right there in Sicily. They grow the raw crystal, they slice the wafer, They etch the chip, and they package the final module.
Which gives them a massive advantage.
Complete control over the quality and the cost down to the atomic level.
And they certainly aren't the only ones making big moves. The research also highlighted Infineon in Germany. They're a giant in the space, and they just bought up GaN systems to lock down that side of the tech. It really seems like the European auto industry is desperately trying to lock down this specific chemistry.
They have to. It used to be that car companies competed purely on mechanical engineering. Who could cast the strongest aluminum engine block or tune the best exhaust note? But today, the battleground is literally semiconductor chemistry.
Whoever has the best crystals wins.
Exactly. If you have the best inverters, you have the most efficient car. There's another company called Marelli, also heavily mentioned in the research. They take these raw chips from places like STMicro and build the finished complex inverter systems for luxury brands like Ferrari and Maserati.
So that brand new electric Ferrari driving down the street is blindingly fast, not because of a V12 engine, but because of advanced chemistry.
Precisely.
Which brings us perfectly to the so what for you, the listener. We've spent a lot of time talking about band gaps and switching losses in Italian factories. But if you are going out to buy a car in 2026 or even just driving one right now, what is the actual tangible benefit you are going to feel?
There are three main tangible benefits that change the daily experience. First is curing range anxiety. These new materials can straight up add roughly 10% to a vehicle's range.
And just to clarify that point, because it's important,
Yeah.
that is 10% more range without making the battery pack any bigger or heavier.
Correct. It's found energy. It is energy that in an older car used to be wasted as pure heat, but is now actually being used to turn the wheels.
Incredible. And the second benefit?
Charging speed. If you actually want to road trip an EV across the country, you want 800-volt charging. You want to stop for coffee for 15 minutes, not sit in a parking lot for 40 minutes. Silicon Carbide is the core enabler for that entire ultra-fast network.
Right, because if the car's internal hardware can't handle the high voltage, that fancy fast charger outside is totally useless.
Exactly. The car will bottleneck the charger.
Okay, and the third big benefit?
Cost. Now, I know this sounds counterintuitive because I just spent 10 minutes saying how incredibly expensive these synthetic materials are to make. And they are right now.
Right, silicons is way more expensive than standard silicon.
But because the wide bandgap inverter is so drastically efficient, you can make the heavy cooling system much smaller. You can make the battery pack slightly smaller while keeping the exact same range. You remove physical weight from the vehicle.
So the total manufacturing cost of the car actually goes down, even if the brain inside it costs a bit more.
Exactly. It optimizes the economics of the entire vehicle system. And the sources point out that right now in 2026, the cost of the chips themselves is actually crashing.
Due to mass production.
Yeah, they're finally moving to larger wafer sizes, 200-millimeter wafers, which means they yield more chips per batch, making them significantly cheaper to produce at scale.
It's a complete virtuous cycle.
It really is. And the exciting part is that it isn't just cars. The research only touched on this briefly, but this wide band gap tech is rapidly trickling down into everything. Electric bikes, home solar appliances, even massive data centers.
Just imagine an e-bike charger that is the size of a matchbox, fits in your pocket, and fully charges the bike in 20 minutes.
That is exactly the gallium nitride promise.
Yeah.
It fundamentally changes the physical form factor of power delivery.
It really does change your entire perspective on what a vehicle actually is. You look at a new EV driving by and you naturally just think, oh, big battery. But really the actual magic is happening inside the switches.
The battery is literally just the dumb fuel tank. The inverter is the actual engine. And what we are watching right now is the industry upgrading from a clunky steam engine straight to a precision jet engine.
That is a very powerful image.
It fits perfectly.
So to concisely wrap up this episode for everyone listening, we are witnessing a silent changing of the guard in technology. The old, sweaty, leaky, inefficient silicon chips that built the first wave of electronics are being rapidly retired.
And they are being replaced by these alien lab-grown crystals, silicon carbide and gallium nitride, materials that can handle intense heat, handle extreme electrical pressure, and move massive amounts of energy with almost perfect, flawless efficiency.
It's basically the difference between a frantic orchestra conductor who is just waving his arms wildly and sweating through his shirt versus a master conductor who is perfectly cool, totally precise, and somehow conducting the entire symphony at double speed.
That is absolutely the perfect summary of the transition.
I think the biggest final takeaway for me here, and something to really chew on after this deep dive, is that the entire future of global transportation isn't just about mining lithium for bigger batteries. It's actually about advanced molecular engineering.
Oh, totally.
We are essentially turning cars into giant high-voltage laptops, which makes you wonder if our entire global electrical grid is going to need to be completely rebuilt from the ground up using these exact same crystal materials just to handle the load of millions of cars charging at once.
That is a whole other rabbit hole, but
Yeah.
absolutely, the grid is next.
The next time you see an EV glide silently past you on the street, don't just think about the heavy lithium block under the floor. Think about the billions of tiny microscopic crystal switches flipping millions of times a second, managing an absolute flow of lightning without ever breaking a sweat. That right there is the real modern engineering marvel.
Could not have said it better myself.
A massive, clear thank you to all our listeners for tuning into this specific deep dive. We really hope this gave you a brand new appreciation for the invisible chemistry that is quite literally driving our world forward.
Thanks so much for listening, everyone.
We will catch you on the next one.